When studying waves, one concept that comes up in sound most often is called the Doppler effect. And the Doppler effect, in its most fundamental terms, is that the frequency of a sound can be affected by motion. Now, the interesting thing about the Doppler effect is that that motion can be both the motion of the observer, VO in this case, or the source of the sound, VS. Either can be moving at a particular speed, and what matters is what direction they are moving and how fast they are moving. And so in this particular formula, it covers all bases. So just to define these terms, F prime is the new frequency, or the shifted frequency. And then obviously F would be the original frequency. V is simply the speed of sound through the medium in which you are measuring the effect. This could be typically in air, 343 meters per second, but this also does occur in water, where the speed would be much higher, 1,440 meters per second. There can be air temperature, water temperature, etc., and this would also work for any other medium, although the typical examples often deal with air and or water. And then your two VS's or your two other velocities here, keep in mind this is both V, the speed through the medium, and then VO and VS are, as I stated at the beginning, this is the observer's speed, this is the person perceiving the sound, and this VS would be the source's speed, which would be the object or person generating the sound. Keeping track of these terms, this formula has functionality for any and all possibilities by combining some interesting notation here with the signs. If you note, on top it's plus, minus, and on bottom it's minus, plus, and that is very on purpose. In this case, it's important to remember that not only does the speed matter, the overall magnitude of the speed, but also the direction. And so rather than keeping with a frame of reference, positives and negatives, this is why I've defined them as scalar quantities, speed rather than velocity, what matters is whether or not they are moving toward or away. And so in this particular format, we would choose the top signs for toward, and the bottom signs for away. And so it's very possible for the observer to be moving towards the source and the source to be moving away. And there's obviously possibilities of them moving towards one another and away from one another as well. And so you have to be careful to first read the problem to decide who is moving, the source or the observer, and then what direction they are moving. And you'll see some examples when you do your homework. Fundamentally, just to kind of go over how this is actually working in practice, is if we think about sound as a longitudinal wave, that means that there are compressions and rarefactions propagating through the air. A compression is an area where the waves are compressed together, and a rarefaction is an area on either side where the air is being spread apart. And so if we imagine that we put this on top of a moving object, like a car of some kind with a big horn playing the sound outwards, as the source moves forward, it pushes on the air directly in front of it, causing it to become more compact. That compression causes an overall increase in the frequency of the vibrations of the particular sound. Whereas if this were moving in the opposite direction, slide this down just a little bit, if the source of the sound, just a horn for exaggerated sake, is moving this direction, then the waves, the air waves being created here, are going to be separated out further away from their traditional or their original state back here, as the air is literally pulled away from the sound moving this direction. And so as we move away, we cause a rarefaction or a decompression of the sound, which ultimately lowers the pitch or the frequency. And now the interesting thing about the Doppler effect in general, the reason why the formula has to account for both the source and the observer, is that this distortion of the air at the source is not the same type of distortion that would occur if the observer were over here. And so if the observer is sitting stationary, then the higher pitch or lower pitch is simply due to that changing of the air at the source. But if the observer is moving, then the air is again being changed near the observer. And so if the observer were to move towards the source of the sound, that would cause the air in front of them to pile up, which ultimately causes the frequency to increase. And if the observer were moving away, then this would do the same kind of effect as your source, which pulls the air apart, causing a decompression or a rarefaction, which lowers the frequency. But since the sound is being distorted closer to the observer as opposed to near the source, the distortion is not the same. This is essentially what we call asymmetrical. So there is an effect of increasing or decreasing the frequency, just as there is an increase or decrease as the source moves, but those two values are not necessarily the same. And with some simple calculations, plugging in a similar speed for either for the source or the observer and towards or away, you'll see that the F prime, the new frequency or the shifted frequency, tends to vary in your results just a little bit depending on which one of these two is moving. And so it's important to keep those straight. Draw a good picture and you should be fine.